Okay, so we have this warm-up question, and a couple of people texted or chatted that they got A equals 1 and B equals 1 for this question. And it's correct. Yep, the convenient values ends up being fractions, half and a third, so it seems like it's not going to work out so nicely. But we can check that the answer is right by actually adding 1 over 1 minus 2x plus 1 over 1 minus 3x, and the common denominator would be 1 minus 3x plus 1 minus 2x, and the 1 and 1 would become the 2, and the minus 3x and the minus 2x would become the minus 5x. We will run into this expression later on in this lesson, and we'll be able to then say, well, if we ever run into this expression, we will be able to replace it with this. Today is the last day of partial fraction decomposition. We spent 2 days learning different techniques, and I mentioned that in calculus, it's used a lot when it's easier to analyze an expression after it's been split up. Sometimes the pieces are easier to analyze separately. But I actually do have a couple of, I think, kind of really clever, interesting applications of this that I want to show you today. One of them is going to rely on, if you remember, what is the formula for the sum of the first n natural numbers. So there's number 1's got numerical answer, and number 2 is something that is in terms of n. What is the answer to the first question? Or how can you calculate the answer to the first question? Okay, so I see that 101 is involved. It's not 101 over 2, which would only be a little bigger than 50. But I see Talia's got the formula n times n plus 1 over 2. And that's right, it's a very famous formula. The 101 comes from adding the first and last terms. And then you notice that if I go to the second and second to last terms, those will also add up to 101. And the number of 101s is going to be 50 times 101, which is 50/50. In general, the first plus the last term is n plus 1, and the number of terms is n over 2. So this is a formula that will also come in handy. Here we go. Let me fix that. That's a formula that's also going to come in handy today. When you add up consecutive numbers, like 1 or 1 plus 2 or 1 plus 2 plus 3, so the numbers 1, 3, 6, 10, traditionally those numbers are called triangular numbers. Just like 1, 4, and 9 are square numbers. But we still often talk about this being a square and that being a square. Well, the reason it's called a square number is because you could literally arrange 4 dots into a nice perfect square and 9 dots into a nice perfect square. Back when they called 1, 4, and 9 square numbers, they also back then would call numbers like 1, 3, 6, and 10 triangular numbers, because you can arrange them into an equilateral triangle. And in bowling, there are 10 pins. And we could take the number 10 and arrange it into an equilateral triangle. So the sum of the consecutive integers create these triangular numbers. So in the 1600s, a great mathematician who was one of the co-founders of calculus Leibniz. I don't think it's just a Z, but actually it looks better with a T. When Leibniz was younger, he was being tutored. I forgot by who. And this infinite series question was posed to him. What is the sum of 1 plus, that shouldn't be a 2, that should be 1 plus 1/3 plus 1/6 plus 1/10 plus 1/15 dot, dot, dot. Anyone want to make any observation about the denominators? And yes, Emily says they are triangular numbers. Now, this sequence is not a geometric series. We have formulas for geometric series, but this is not a geometric series. The first term times 1/3 is 1/3, but 1/3 times 1/3 is not 1/6, it's 1/9. So this is not, we can't use geometric series formula to find this. So the sneaky trick to this problem is that each term, in general, each term is 1 over n times n plus 1 over 2. That's what all the terms are. In other words, this 3 is 1 plus 2, and this 6 is 1 plus 2 plus 3. So every single term is uses the sum of the integers, which is the triangular numbers. So each term has this structure to it. And you could plug in 1 to this formula, and you'll get 1 out. And if you plug 2 into this formula, you get 1 over, sorry, if you plug 0 into the formula, you would get 1. If you plug 1 into the formula, you would get 1/3. Would you? 1. I got myself a little bit confused. 1 times 2 over 2. No, sorry about that. So if you plug 1 in, you do get 1. And if you plug 2 in, that's where I got confused. 2 times 3 is 6 over 2. Yes, if you plug 2 in, you get 1/3. And if you plug 3 in, you get 1/6, and so on and so on. Yeah, 0 produces an error. So the trick to this question is to take the 1 over n times n plus 1 over 2. Each term has that pattern to it. And we could flip it because it's 1 over. And what does this look like, something we might be able to work with? What seems like a thing we could do and might lead somewhere? What have we been doing exclusively for the last couple of days? Partial fraction decomposition. Thank you. A over n. It's an n instead of an x, but would you go ahead and do the partial fraction decomposition and get the values of a and b? There you go. So we ended up with 2 and -2. Well, what good is that? Well, if this identity is true, 2 over n times n plus 1 equals 2 over n plus 2 over, sorry, minus 2 over n plus 1. If I plug a number like 1 in, then I get 2 over 2, which is 1, is equal to 2 over 1 minus 2 over 2, which is true. But if I plug n equals 2 into this, I will get 1/3 is the same thing as 2 over 2 minus 2 over 3, which is 1 minus 2/3, which is true. I'm going to write this as 1 minus 1. And just to see what's going on, when I make n equals 3, I get 2 over 12, which is 1/6, which is equivalent, according to the formula, of 2/3 minus 2/4, which I'll write as 1/2. And 2/3 minus 1/2 is 4 over 6 minus 3 over 6, which is 1 over 6, which is true. So what does this all have to do with the sequence? It means this 1 can be written as 2 minus 1. And the 1/3 can be written as 1 minus 2/3. And the 1/6 can be written as 2/3 minus 1/2. Does anyone see what's going on here? It might even be better to leave it like this, and I think I will. I'm not going to reduce the stuff. 2/3 minus 2/4 plus 2/4 minus 2/5. That's the next term. Yeah, I think this will be easier to see if I don't simplify. Okay, does anyone see what's going on? The next term is going to be 2/5 minus 2/6 plus dot, dot, dot. Now that I've turned this 1 plus a third plus a sixth plus a tenth into this form, does anyone notice anything? And Ethan says it just becomes 2, which is right, because what happens here is that the minus 2 over 2 cancels out with the plus 2 over 2, and the minus 2 over 3 cancels out with the plus 2 over 3, and so on forever. Which means the answer to this question is 2. They call that sometimes a telescoping series. Long ago, there were these like telescopes that would sort of fold up into like a little thing, and then that's what this is like when these cancel out. So telescoping series, and it had a surprising use of a partial fraction decomposition was like the key insight that allowed that to happen. So you see, there is an application of partial fraction decomposition besides the kind that we'll see in calculus next year. Okay, now I have a second application. And I'm just going to warn you that this is one of the more confusing things of the entire semester, what we're going to do over the next 25 minutes. I find it to be, but it's extremely clever, and I think you'll like it and be surprised by it, and it will have an opportunity to use partial fraction decomposition. Okay, and it has to do with finding the nth term of a sequence. Now, here we have a famous sequence, 1, 1, 2, 3, 5, 8. And what's the story with this sequence, and what's the next term? You could type it into the chat. And that's right. The next term is 13. This is the so-called Fibonacci sequence. So 13 is next, because 5 plus 8 is 13. And then 21 is 8 plus 13, and 34, and so on. So it's easy to find the next three terms. But finding the 100th term is very difficult, because the only method we have for this is to work our way up. We don't have a direct formula that you could plug the number 100 into, and out comes the 100th term. But there is a formula for it, but it's very complex. Often we write sequences like this. You might remember from Algebra 1, they had recursive sequences where they kind of tell you the first term, or in this case, the first two terms. And then they give the recursive definition, where they tell you how to find additional terms. But again, looking at a sequence and maybe knowing the recursive definition is good if you're just looking for the next term or the next few terms. But if you want to jump to the 1000th term, even with this recursive definition, you're not going to be able to do it easily by hand. Now that sequence, Fibonacci sequence, we will be able to find the 1000th term using the method I'm going to teach you now, but there's easier examples than Fibonacci numbers for this process, so I'm going to show you it for a different sequence. A harder sequence, but the process works out more nicely for it. Here is a sequence. You see the first 5 numbers, 2, 5, 13, 35, 97. It is unlikely that you'll be able to figure out quickly what the next term is. But just for fun, anyone have some ideas about what the next term is? Take a minute. You could do some chat on it. Oh, wow, I see someone got the right answer, which is 275. Leo, did you notice a relationship, like how to get from two terms to the next one, or some other relationship? Because there's two ways to get to this thing. One is the recursive relationship, which is hard to see. And then there's also a direct formula. Leo, what'd you get? I see you have the right answer, so you must have n minus 1 to the third minus, Okay, that might work also, might be equivalent. I will tell you, though, that the recursive definition for this one was A1 equals 2 and A2 equals 5. Well, of course, those are the first two. But kind of like Fibonacci, the rule was instead of adding the last two numbers together, we multiply the previous number by 5 and the two numbers before by 6 and then subtract. Now, good news for you, you're not going to have to figure out what the sequence is like that, like what the rule is. You'll actually be told what the rule is. You'll have to do something even more difficult than that. How to take that rule and turn it into a way of finding like a specific term, like the 100th term or something like that. But with this, you can find at least the next term by doing 97 times 5 minus 35 times 6. And you do get 275. Again, good news, you do not have to figure out these. Those will be given to you. So Leo, yours is going to be like the direct one, and it did seem to work. So it seems like it's equivalent. I'm going to get to with the like a process for coming up with the direct one in sort of another form than what you have. It's interesting. Yours with the n-1, a times n-1 to the third. So Leo, yes, you did get a direct one. It's not exactly the same one that I'm going to show you how to get, but it will work. What you got does work. Okay, everybody, here it comes. One of the most this is one of the more difficult things that we learn the whole year, this process, but it's a really clever process, and I think you'll like it. So here's the way the process goes. I am going to create a strange function. And this is the only other question we have today. So this question takes like 20 minutes to do. And the way this function works, it's like a polynomial where 2 is the first term, and the second term is 5x, and the third term is 13x squared, and the next term is 35x cubed. So I have this, it's like a polynomial function, but it's infinite. And the coefficients are the numbers in the sequence. Now, since we know that each number is equal to 5 times the previous number plus 6 times the one that's 2 before. Okay, that's given to us. So 13 is 25 minus 12. I'll write that. 13 is 25 minus 12, which was 5 times 5 minus 6 times 2. And that's true for every pattern, for everyone. I'm going to do something kind of funny here. I'm going to say x f of x, sorry, 5x f of x. If I multiply each term by 5x, the 2 becomes 10x. The 5x becomes, I'm sorry, could you please make that negative? Let me erase that. So negative 5x f of x. And I did negative 5x because it has to do with the fact that, well, let me show you how it works. You'll see why it's negative 5 in a second. Negative 10x, 2 times negative 5 is negative 10x. 5x times negative 5x is negative 25x squared. And negative 5 times 13 is negative 65x to the third. And here I'm going to say plus 6x squared f of x. Notice how the 5 and the 6 are like the two numbers that are involved in this rule. except I used -5 and +6. I kind of used the opposite sign. I'll show you why that happened in a second, but let's see what happens if I take this original f of x and multiply everything by 6x squared. I would get plus 12x squared. That's 2 times 6x squared, and then plus 30x cubed. Okay, does anyone have an idea of what I can do with these three lines? I have f of x, -5x f of x, and plus 6x squared f of x. Look carefully at the three numbers in each column. And yes, Patrick says add them, and that's right. Because when you add them, almost everything cancels out, except for 2 minus 5x on the right-hand side. On the left side, I get f of x minus 5x f of x plus 6x squared f of x. Okay, does anyone see anything that I can do to, anything I might be able to do with this? I do have a lot of f of x's here. Any thoughts of what? Yes, solve for f of x. If I factor out the f of x on the left, I get 1 minus 5x plus 6x squared equals 2 minus 5x. And then if f of x times 1 minus 5x plus 6x squared equals. And now if I divide both sides by 1 minus 5x plus 6x squared, I get this f of x equals 2 minus 5x over 1 minus 5x plus 6x squared. And as Riley said, remember in the do now, because this thing factors to 1 minus 2x, 1 minus 3x. Doesn't always factor. If it doesn't, you have to use the quadratic formula and do some kind of, it gets really complicated. So I made this one so that it did factor. Ethan asked about the -5 and the +6. Those came from the rule. Because each term was equal to 5 of these minus 6 of these, if I do +6 of these and -5 of these, it will turn it into 0. If you subtract, because 35 was because 13, was -5 times 5 plus, since 13 was 5 times 5 minus 6 times 2, that would mean, so if 13 is equal to 5 times 5 minus 6 times 2, then 13 minus 5 times 5 plus 6 times 2 would equal 0. And that's why, yes, you do switch the signs of the coefficients. Okay, so here we are. And it happens to become 1 over 1 minus 2x plus 1 over 1 minus 3x. So now I have the function in this new way. Now remember, the goal is to figure out, we're trying to figure out what the next coefficient is. And this thing, whoops, where is it? This thing really does not look so much more useful in finding the coefficient of the x to the 5th term or something like that. It actually seemed like we were in better shape, over here. But there's one more trick. There's one more trick coming. Okay, shift gears for a second. Do you remember this from last semester? Infinite geometric series. What is the sum of an infinite geometric series with a first term of A and a common ratio of R? Anyone recall what the formula is for that? And maybe specifically, what's the answer for the 2 plus 2/3 plus 2/9? It's one of the shortest and greatest formulas in all of math. A plus AR plus AR squared. It is, Umer, A over 1 minus R. Incredible. Infinite geometric series. So A is the first term, R is the common ratio. So 2 over 1 minus, sorry, it's 1/3 is the common ratio. So 1 minus 1/3 in this case is 2 over 2/3 equals 3. So this formula, A plus AR squared forever equals A over 1 minus R. And usually we go in this direction. We're given an infinite geometric series and we use the formula. But you can actually go in the other direction. If you have something that looks like A over 1 minus R, you can turn it into the geometric series. So if I have something like 5 over 1 minus 1/5, I can turn that into A plus AR plus AR squared plus ... 5 plus 1 plus 1/5. Well, now let's go back to where we are. Are we? We're over here. We'll look at these two things. They look like A over 1 minus R, which means they can be expanded. Let me get a new page for that. F of x equals 1 over 1 minus 2x plus 1 over 1 minus 3x. So what does 1 over 1 minus 2x, what's the first 3 terms, or the first 4 terms of that expanded back into a infinite geometric series? What's A and what's R? That's right. A is 1, 2x is R. So it becomes A plus AR plus AR squared plus AR cubed plus ... But there's also this second thing that has the form A over 1 minus R. And if I write that one underneath, I would get 1. This one, A is 1 again, but R is 3x. So 1 plus 3x plus 3 squared x squared plus 3 cubed x cubed plus ... And when I put those together, I get 2 plus 5x plus 13x squared plus 35x cubed. But more importantly, I can see that the if this is the first term, second term, third, fourth, the nth term would be 2 to the n minus 1, x to the n minus 1, 3 to the n minus 1 times x to the n minus 1. See, because 13 is 2 squared plus 3 squared, and 35 is 3 squared is 2 cubed plus 3 cubed. So that means that the 11th term would be 2 to the 10th plus 3 to the 10th. And in doing so, I could jump, or the 100th term is 2 to the 99th plus 3 to the 99th. So this enables me, this process, this whole complicated process, it started with the definition of the recursive sequence. You had to be told this. I mean, if you weren't told it, maybe you'd figure it out with enough trial and error, but I'll be telling you what the relationship is. That eventually turned into this really complicated process where we made this polynomial that had the coefficients matching up with the numbers in the pattern. And then this really clever use of the relationship between the coefficients to create this simpler version of it, which led to a partial fraction decomposition. That's why I'm teaching it to you today. It's application of partial fraction decomposition, and we got this. The last step is that I took each of these things, and especially because there's a 1 here, and use the a over 1 minus r formula in reverse. If this wasn't a 1, if it was a 2, for instance, I would just reduce this fraction by dividing top and bottom by, or multiplying top and bottom by a half. So what happened here, when I expanded this guy, I got this expression. When I expand this one, I got this expression. And then when I add them together and combine like terms, the 2 and 3 get added together to become the 5, and the 2 squared and 3 squared become the 13, and the 2/3 plus 3 to the 3rd becomes a 35. But now I have the general, the 2 to the 10th, 3 to the 10th. Well, because I'm calling this the first term, and this is the second term. The second term has an exponent of 1 on all of these, including the 2 and the 3. So the 10th term would be the x to the 9th, and it would be 2 to the 9th and 3 to the 9th. Yeah, we do. We end up adding them together because of this plus right here. Oh, maybe you think I'm trying to add. I'm not trying to make stuff cancel out. If I had more room, I would have written this all on one big line. But because I ran out of room, I put them. It's actually not bad to have them next to each other in this way either. But I did. I added the two things together because of this plus. And when I add them together, I get the 2 and the 5 and the 13 and the 35. Yeah, it looks like I'm going to subtract them and make stuff cancel out, but I'm adding them together. And that is the new thing. Pretty intense, I have to admit. I have a practice one for you that you can chat about. Let me find it. Where is my question? Hold on. It's actually in the homework, so let me grab this here. Okay, the challenge question. This is going to be a homework question, so you don't have to do it right now. But let me just write it up just for the sake of the video. So the sequence looks like this. It's totally not obvious that A1 is, well, the first two terms are. See? The general pattern is 10 a n minus 2 plus 3 a n minus 1. Again, that is not, you're actually given that. And the question is, the challenge is to come up with a formula for the nth term of this sequence. And it's going to be it's going to involve like things being raised to powers. I'm going to stop the video now.